Okay, so we're going to do a couple more examples for section 5.1 in a little bit more detail than I did the last one. I'm going to split this up. So this one's just about finding area of something that's underneath the curve, and we're just going to look at approximating it and kind of see what we're going to be doing here shortly. So let's suppose for a second that we've got a function x squared, okay? And we want the area under the curve from x equals 1 to x equals 5. Okay, so picture-wise, what we're looking for then is we've got this function that we've graphed. We're looking at just part of the parabola here. So that's my x squared, right? And what I'm looking for then is where that's 1 and this goes to 5, we're looking for how much area is there between the x-axis and the curve. So what we're going to do then, we approximate that, and we have to decide how many intervals that we're going to break things up to. And like we discussed, we can use, the more intervals that we use, the more accurate that approximation is going to be. So let's just say number of intervals, okay? So n, when we do this stuff, is the number of intervals. So, and let's just say that n is going to equal 8 in this case. Okay? Now, what do we do with this? Okay, well, first, remember we're making a bunch of rectangles in here. Okay. So we're going to make 8 rectangles. See, 1, 2, 3, 4, 5, 6, 7, 8. So there we go. So 2, 3, 4. So if we want to know the width of our intervals, that's what we usually denote as delta x. And we're just going to take the right endpoint minus the left endpoint and divide it by how many intervals that we want. So that would be 4/8, so 1/2. So each of our rectangles has a base that's 1/2 unit long. Okay. Now, the other thing that we have to do is decide how tall our rectangle is going to be. And we have different methods of doing this. In the end, you just have to pick what's called a sample point. Okay. Now, that sample point in all of the formulas and stuff has a little asterisk beside of it. Okay. So it's going to be x star, and it might have x1 or x2 or whatever it is for the first interval, second interval. So we just have to pick a point in the interval, and we're going to evaluate that point, okay, to find the height. So the height of the rectangle is whatever our function is evaluated at that sample point. Now, we discussed a little bit, we could use the right endpoint, the left endpoint, the midpoint for all of those things, and those are just a matter of convenience. It could really be any point inside of the interval, okay? So what we're going to do is we're going to pick, let's just say the left endpoints, okay? So let's use left endpoints. So looking at our intervals, we start off at 1, and then we go to 2. So there's our first interval, is from 1 to 1.5. The interval on the left, the endpoint on the left is the 1, right? So if I want to approximate the area, then I'm going to look at just the area of a rectangle. It's base times height, correct? So we have this rectangle here, okay, that I'm not very good at drawing, so it should have been The height of the rectangle there is at the, there we go. So for this first little rectangle, the height of it is, we'll evaluate it at f of 1, and then we multiply by delta x, right? Okay. Now I'll substitute values in here in a second, and then f of 2 would be the next little rectangle that we put into there. So that would be the height of that rectangle, and then of course we multiply it by delta x. And we do that for, oh, that shouldn't be 2, that should be 1.5. My apologies, so 1.5. And then the next one we're at 2 times delta x. And then we work our way all the way down until we get to this last rectangle here that starts at 4.5. So just to simplify the little calculations when I type things in and stuff like that, notice all of these things have a factor of delta x, which we already know is 1/2. But we can always factor that out. We just get f of 1 plus f of 1.5 plus blah, 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 all the way down till we get to the 4.5. So that's 1/2. Now we're just squaring things, and we're going every half. So that's 1 squared plus 3/2 squared plus 2 squared plus, what, 5/2 squared. That's 2.5. And 3 plus 3.5 squared plus 4 squared plus, oh, I'm running out of room, 9/2 squared. Okay. Okay, now adding all that stuff in the parentheses up, see, I'm getting 71. So my area, and these should little be approximates. Okay. So my area is approximately 71/2, or if you want to think about that as a decimal, 35.5. Okay. Now, I just chose the left endpoints just because that's the one I wanted to use. Okay. I could do the same thing, and I could use the right endpoints. Okay. That's actually not going to alter things a whole lot, but just to go through it with this same function, if I use my right endpoints, then again, just to have kind of the little picture here with us, then these sample points, if I start at 1, 1, 2, then when I go to draw these rectangles, the height of it is going to be used on the right side. So I'm going to have my first rectangle is going to be there. My second rectangle will be up here. And notice the height of the rectangle then starts at 1.5. Okay, because we're using the right endpoint of it. So when I make my calculations this time, we still have that same delta x, but now it's f of 3/2, okay, plus the function evaluated at 2, plus the function evaluated at 2.5, because we're just moving over half each time, all right? Plus all the way down until we get to the last one, which would be at f of 5. Okay. All right, so when I add all of those up, let's see, all the way till we get to 5 squared. So this one would be 95 over 2 for my approximation. Now notice that one's too big, but like we discussed last time, that's okay. This is an overestimate of it. Now, ideally, what we do when we find the area then, if we want to know exactly what the area is then, we have to take that interval, okay, there's my x squared, okay, and we have to have more and more intervals in there, right? So if we start at 1 and we go to 5, and then we tack in some intervals, and then we tack in more intervals, right, to make smaller rectangles, and then we make smaller and smaller and smaller rectangles, what are we doing there? All right, a bunch of little tiny rectangles, boom, 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 all the way down. So more and more rectangles means n is approaching infinity, correct? So, something's approaching something. God, it's one of those awful limits. So in a nutshell, what we're looking at is n approaches infinity, okay, of delta x times our function evaluated at the first little sample point, okay, whether it be right, left, midpoint, some other arbitrary point in there, plus the function evaluated at the second little rectangle, right? So these subscripts are really just talking about which rectangle we're doing the height of, all the way until we get to the very last one, correct? So that's the limit that we're actually looking at to find out what the area actually is. Now, we're not going to be computing a lot of these, but with x squared, it's actually not horribly bad because we do have a formula for squaring something, which we could do, but I'm not terribly worried about it right now. As a notational thing, that's supposed to be an M. That just looked like M100, didn't it? N approaches infinity, delta x. Now, you'll see this sigma notation that looks something like that. That doesn't look like a delta. Now that sigma notation just means you're going to sum, right? You're going to add it up, and then each time you're going to replace I with the next little integer. So the first time you'd have I1 plus f of x star I2 until you get up to n. So I'm just writing in a shorthand. That's what this is right here, okay? So just to do this little limit, the formula for adding up a bunch of squares, okay? So as a little side note, if I wanted to add up from I equals 1 to n a bunch of things that are squared, take n times n plus 1 times 2n plus 1 and divide that by 6, okay? That would actually be the formula for adding up a bunch of squares. So let's go back to our little area. If I want to find out exactly what the area is, then I look at the limit as n approaches infinity of my delta x in this case was always 1 over n, right? Okay, and then we would have the sum. Now, this function, remember, is x squared, okay? And each little endpoint, okay, is something over x, something over n, x squared, right? So the question I have, okay, is what do we have going on here? that shouldn't be 1 over n. I had, since I was going from 5 to 1, and we had 8 intervals, it should be 4 over n. If I can get this to erase. So let me write this thing out. So let's stick with our left endpoints. Okay, so that was 1 squared. Plus now the next one, depending on what our interval is, right, is 1 plus, what, 4 over n, just moving over that little bit, whatever the interval width is, right? 1 plus, then we would do 2 of those intervals over. All right, then we would do 3 of those intervals over. All the way until we got to the very last one, okay, which I probably didn't, which would be n minus 1 times 4 over n. That squared, right? Because well, that's how many intervals we have. 1 plus 4 over n squared plus, now let's evaluate that limit. All right, so I'm having some issues with my computer, so let's just end this thing. So in the end, this is going to be 41 1/3. Okay, would be the actual area under this curve. Now you're not going to have to calculate these limits. I was just kind of showing you what's going on in the background and stuff. But what you'll have to do is do some of these Riemann sums, where the height of the rectangle is the left endpoints, the right endpoints, or the midpoints. But just remember, you're doing a bunch of little rectangles. It's just the length, base times the height, and you're adding all that stuff up. So maybe the next one will go a little smoother.